In this lesson, we're going to be solving problems that involve related rates of change, and this is basically an application of the implicit differentiation that we learned last time. So let's just start with an example. In this problem, we're given an equation that relates x and y. And this part is important. They're telling us x and y are both functions of t. So in the past, we usually used the letter x for our input. Now the letter t is our input variable, and both x and y are actually output variables. We are told that when x is 2 and y is negative 3, dx dt, so the derivative of x with respect to t is 5, we want to find dy dt. So again, notice we have little dt's here because t is our input variable, not x. That's how this problem is different from the kinds of notation we've used in the past. So to solve this problem, I'm going to start by taking the derivative of my equation implicitly. So the derivative of 4x squared is 8x, but then I have to multiply by dx dt. That's the chain rule, the implicit differentiation, because x is now an output function. Just like in the past, we had y as our output function. Now we have two output functions, x and y. Then the minus 2xy, I'm going to use the product rule on that. I'm going to say my u is the minus 2x, my v is y. So u prime is minus 2x, so u prime is minus 2, but then times dx dt. And if you want to use x prime here, you can. And my v prime is just 1 dy dt. Again, if you want to use y primes, you can. I'm writing it out in this other notation just to make it clear that the input variable is actually a t. Okay, so using the product rule, we take u prime times v. So negative 2 dx dt times y plus v prime times u. So that's going to be a minus 2x times dy dt. Okay, now the derivative of y squared is going to be a 2y, but then I have to multiply by dy dt. And the derivative of 37 is 0. That's my constant. So I took the derivative of each term. I didn't forget to use the product rule. And because both x and y are output variables, when I took their derivatives, I had to multiply by an x prime and a y prime, although I used the notation dx dt, dy dt. Now you can solve for dy dt, but I think what I'm going to do is I'm actually going to plug all the numbers in and then do the solving. So x is 2, y is negative 3, dx dt is 5. Let's plug those numbers in. So 8 times 2 times 5, minus 2 times 5 times negative 3, minus 2 times 2, and we don't know dy dt, so that just stays as is, plus 2 times negative 3. Again, I don't know what dy dt is. I'm going to do the math and combine like terms. This is an 80 plus 30 minus 4 dy dt minus 6 dy dt equals 0. Combine like terms, I get 110 minus 10 dy dt equals 0. So to solve for dy dt, I need to get it by itself. I guess I'll subtract the 110 from both sides, and then I'll divide by negative 10, and I am left with dy dt equals 11. So the steps that I took here were I took the derivative of every single term, then I plugged numbers in, and then I solved for dy dt. All right, let's see how this works in an example. This problem says the radius of a circle is increasing at a rate of 10 feet per minute. How fast is the area increasing when the radius is 5 feet? So before I start the word problems, I like to make a list of everything I know and everything I want to find. It helps me organize the information. So I know the radius of the circle is increasing at a rate. That's telling me this is a derivative, the rate of change of the radius. So dr dt is 10. Radius is increasing at a rate of 10 feet per minute. I want to know how fast is the area changing. I want to know dA dt, and I'm interested in it at the instant in time when r is 5. So once you have your list, because I see a's and r's, I have to write an equation that relates a to r. And if we're talking about a circle, the equation is a equals pi r squared. Now I'm going to take the derivative of both sides with respect to time. The derivative of a is dA dt. The derivative of pi r squared would be 2 times pi times r, but then we also have to multiply by dr dt. That's our chain rule. After I take the derivative, I'm going to plug in the numbers that were given to me in the problem. So dA dt equals 2 times pi times 5 times 10. That would be 100 pi, and this would be square feet. We're talking about area per minute. Or if you want to put this into a calculator, you could round it to 314 square feet per minute. All right, let's do another example. It says the height of a cylinder is increasing, so we're talking about a derivative, at 7 meters per second. So that's height. So I guess dH dt is 7. And the radius is increasing, so another rate of change. We'll call that one dr dt. The radius is increasing at 3 meters per second. How fast is the volume changing? So I want to find dV dt. When the cylinder is 5 meters high, so when h is 5, and has a radius of 6, r equals 6. All right, so let's see. We know things about h's and r's. We want to find dV dt. So my equation is going to have to do with volume. And the volume of a cylinder is pi r squared times h. Now I'm going to take the derivative of both sides of this equation with respect to t. The derivative of v is dV dt. And on the right-hand side, I have a product. I'm going to use the product rule. I'm going to let my u equal the pi r squared, and my v is h. So u prime would be 2 pi r times dr dt, and v prime would be dH dt. Using my product rule, I take u prime times v, so 2 pi r dr dt times h, plus v prime times u. And once I have the derivative, I'm going to plug in the numbers that I have listed on my paper. So I plug in 6 for r, I plug in 3 for dr dt, 5 for h, 7 for dH dt, 6 for r. And now I'm going to go through and do the math. I could just put this into my calculator. Let's see, I got 180 pi plus 252 pi. That's 432 pi. Or again, if you do want to put this into a calculator and get a decimal approximation, I think it's about 1,357. And for units, we're talking about a volume. We've got meters, so it'd be meters cubed. And our time here is seconds, meters cubed per second. So the volume is increasing at a rate of 1357 cubic meters per second. Example 4, a rainbow trout has taken the fly at the end of a 60-foot line, and the line is being reeled in at a rate, there's my derivative, rate of 30 feet per minute. If the tip of the rod is 10 feet above the water and the trout is at the surface of the water, how fast is the trout being pulled towards the angler or the fisherman? Okay, so before I can list my know and my find, I need to draw a picture and assign some variables. All right, so we've got our water, and our fish is attached to the end of some line. And what's happening is the person is reeling in this line. So the distance, the length of this line is changing. And as this line gets reeled in, the fish gets dragged along the surface of the water. The only thing that's staying constant here is the tip of the rod is always 10 feet above the surface of the water. But the distance that the fish is along the water is changing. as this fish gets closer and closer and closer to the pier, that distance is changing. I think I'm just going to call that distance x. And then the length of the line, this distance here, is also changing. As the fish is being reeled in, that line is actually getting shorter. I think I'm going to call that distance y. Okay, so now I'm ready to list what I know and what I want to find. So the trout is at the end of a 60-foot line. So that's what we called y. So y is 60 feet. The line is being reeled in at a rate of 30 feet per minute. That's my derivative, dy dt. I'm actually going to call it negative 30 because the length of the line is actually getting shorter. It's being reeled in, so it's decreasing instead of increasing. The tip of the rod is 10 feet above the water. We got that. How fast is the trout being pulled in? And so the thing we want to know is dx dt. What is the speed that the fish is moving along the water? So I have to write an equation that relates x and y. And in this problem, I notice that I have a right triangle. Anytime that you have a right triangle, you can use your Pythagorean formula to write your equation. And that's that formula, a squared plus b squared equals c squared. In this case, my a is x, my b is 10, and my hypotenuse is y. So I got the equation x squared plus 10 squared is y squared. Notice because 10 was a constant, I could plug that number in, but y is not a constant, it's changing, and so I can't plug the numbers in yet. All right, so my equation is x squared plus 100 equals y squared. And so now I'm going to take the derivative of this thing. The derivative of x is 2x, and then we have to multiply it by dx dt. The derivative of 100 is 0, and the derivative of y squared is 2y times dy dt. Now I have to plug things in. So we have a slight problem here. I don't actually know what x is. I'm trying to find dx dt, so that's okay that I don't know what that is. I do know y is 60, and I know dy dt is negative 30. So we've got an extra step in this problem. We have to figure out what x is so we can plug that in. And we want to know what is x when y is 60. So I'm just going to draw another little triangle over here. So the height is always 10. When y is 60, what is x? Well, I could use my Pythagorean formula. X squared plus 10 squared is 60 squared. So x squared plus 100 is 3600. X squared is 3500. If I take the square root of that, I get approximately 59.2. So when y is 60, x is 59.2. And so now this is the math that I'm going to do. I'll take this equation, solve it for dx dt. And so I think this time I'm just going to put everything in my calculator at once. And so I'm going to divide both sides by 2 times 59.2. And then just type that into my calculator. And I ended up getting 30.4. And the units would be feet per minute. So the line is being reeled in at a rate of 30 feet per minute, and that's dragging the fish along the water at a rate of 30.4 feet per minute. All right, again, these sections with word problems, they just take practice, but feel free to use the tutors or come to office hours if you're struggling with any of these.